Chapter 16 on integrals and vector fields. Section 16.1, line integrals of scalar functions. So some learning goals here, you should know what a line integral of a scalar function is, be able to set them up and compute them, along with know some applications of scalar line integrals. So what's going on here? What is a line integral of a scalar function? So we're going to be thinking about functions of 2 or 3 variables here. So the sort of functions that we've been talking about in chapters 14 and 15. And the idea here is that we want to integrate this kind of function along some path. And so in 2 dimensions, the idea here is, we have this path here, C. What is the integral of f of xy along this path C from here to here? Or working in 3-dimensional space, we have this path here in 3-dimensional space. What's the integral of f of x, y, z over this path in space? So going back to, the definition of integral in terms of Riemann sums and, adding up lots of infinitesimally small quantities. What we're going to think about, how do we come up with what's the meaning of integral over c of f of x, y ds? Or this one would be the integral over c of f of x, y, z ds. So the first thing I want to highlight here is this ds. We've had integrals that are dx, dy, dz before. We have integrals that are dt before. We've had integrals that are like dA or dV, and we're integrating over chunks of area or volume. What does this ds mean here? This ds is a signal that this is like a small chunk of arc length. And so what we're going to do, like the Riemann sum type definition here, how do we approximate an integral here of f of x, y on this curve C? Let's break curve C here up into different chunks. Here I drew 5 chunks. And what we're going to do is that on each chunk, we're going to pick like a test point, like f of, x naught, y naught for that particular point, x naught, y naught. And then we're going to, multiply by ds here. This is going to be, we're going to multiply by, this delta SI. This is the length of the arc segment. So what we do is that on each of these different little arc segments, we pick a test point there and evaluate the function at that test point. And then we multiply it by the length of the arc segment. Now, what is the length of the arc segment? Well, that can be a tricky thing to do there. So in practice, it just kind of becomes the distance from here to here, using like a 2D or 3D distance formula. Anyways, I'm getting a little bit vague here, a little bit imprecise, so maybe I should show the formal definition. If f is defined on C, and C is given parametrically by R of t is g of t I hat plus h of t j hat plus k of t times k hat, t is running from A to B. So I guess here we're working in 3 dimensions. We're more in this picture than this picture, but just cover up this here to get it down to 2 dimensions. Then the line integral of f over c, integral over c of f of x, y, d ds, is the limit as n goes to infinity, the limit as we, take more and more and more, break this up into more and more and more chunks here. The sum from k is equal to 1 to n, so here we see the Riemann sum definition going on here. F of x sub k, y sub k, z of k, there's our test point, times delta sk this is the length of, of arc segment number k. Okay, so this is our formal definition here, and so we're taking this as, we have more and more and more of these line segments. We're making these smaller and smaller and smaller. This isn't a very computationally useful, let me recenter this. This isn't a very computationally useful way to evaluate the integral, right? We really don't want to have to do this. And so in practice, how do we do this? Because we don't want to have to evaluate a Riemann sum every time we have an integral here. To integrate continuous function f of x, y, z over c, okay, so once you have your smooth parametrization of c, the actual way that we're going to evaluate this is take your parametrization, plug it into the function here so that, that this makes sense. This makes sense here on plugging in the parametrization into the function because, this is t is equal to a here, this is t is equal to b here. So if this is t1 right here, r of t1 gives you that point on the curve. And so then f of r of t1 gives you the point on the curve. Plug in r of t1 into f, that gives you the function, function value at that point right there. So as t runs from a to b, we're going to be running through all these different function values. And there's one more thing that we have to take a look at here. The absolute value, or really in this case, the length, the magnitude of v of t, where this is the magnitude of r prime of t, for this parametrization r of t up here. Where is this coming from? Well, this is what's going to do the arc length. So the thing that we should the thing that we should remember is how do we calculate out the arc length of a curve? Integral from a to b of the magnitude of r prime of t dt. This gives us the arc length of the arc length of a curve that's defined by r of t, where t runs from a to b. And so this factor right here, the length of arc segment number k, in the limit, that becomes the magnitude of r prime of t dt. And so that's where this formula comes from. So in the next couple of videos, when we start to actually evaluate scalar line integrals, we're going to jump straight to this formula here because we don't want to have to do a Riemann sum every time we evaluate the integral. But that shows where this that shows where this formula comes from.